Now I will show you one example that how we can use a low pass filter to increase the width of a signal. Say we have a time domain signal here that's shown in the red data. This is the time domain signal, and this is the time domain signal, and we wanna increase the width of the signal. So how can we increase the width of the signal? That's our goal, to increase the width of the signal. And basically we want something like this, that the width of here to here in time domain is increased. So this is the after doing the low pass filtering, and the red one here is the before low pass filtering. Actually our goal is to use the low pass filter and to increase the width of the signal. That's our goal, and we'll see how can we do that. So to do that, we can use different type of low pass filter. For our case, we use the low pass filter that is sold by Thorlab. So the characteristics of the Thorlab filter is something like this. This is the frequency response, and you can see the different kind of frequency here. X-axis is the frequency, y-axis is the relative response in dB. So we will use this frequency range to filter out some of the high component of the frequency, and if we remove the high component of the frequency, then our signal width will increase. So that's the goal, and I will show how to do that in MATLAB. So actually the step that I will follow are here. So these are all your time domain signal. Say for example we will take this one as the input. If we convert in frequency domain, and this is the half signal, so we will be able to see this is the frequency domain signal. Now just for in case like you are doing everything right, I have done the FFT of this signal just to see can I come back the original signal. So that was our original signal, and after doing the FFT and inverse FFT just for check, we can find the IFFT. We can find the original time domain signal. Now this is the filter response of the Thorlab filter, low pass filter. This is the low pass filter response. So here this axis is in dB, so this is in dB, but if we convert from dB to normal scale, so the signal response will be something like that. Now so if we do the FFT of any signal, so you will have a lot of frequencies, but in the low pass filter that we will bought from the Thorlab, it can only work on certain frequency range. So whatever the initial frequency of the time domain signal of our input data, we will not be able to use all. So we will only allow those frequencies that are within the range of our low pass filter. So then what do you need to do? We need to only collect the data for the frequency range of low pass filter matches with the frequency range of our original data. So to do that, to match exactly, as we know that we have done sampling differently. So if we do the sampling differently, that means the x-axis of your original data, that is the frequency data, is totally different than the x-axis data of your Thorlab low pass filter. So we have to match. So the way to match is we have to do the interpolation. So if we interpolate the original data into the Thorlab data, that means actually we are trying to get the Thorlab response, Thorlab frequency and corresponding response exactly match with our time domain or exactly match with our frequency domain data. Then we can multiply and figure out what will be the response. That's why we did the interpolation. After the interpolation, actually we changes the x-axis of the Thorlab data. So actually if you look at the both of the graph of the Thorlab normal, this one and this one, they look similar, but the x-axis actual point in the matrix, it will be different. It will be different because you are just interpolating to match with our original data. If you plot in log scale, it will look like that. So frequency response will start from here, say 4.5 to 6.7. Originally it was something like that, and the final result will be something like this. So let's go to the example. So these are the steps now I will do. So just to summarize, how will we proceed? We have a time domain signal. We will do the FFT of the time domain signal. So we will find the frequency. So that's step 1. And in step 2, we have a Thorlab low pass filter. It has a frequency response. We have to do the interpolation of the Thorlab low pass filter data because we want to exactly match the frequency of our time domain signal with the Thorlab signal. So we'll do that, and then we'll take the exact response of the low pass filter, and finally, so these are all we are doing in frequency domain. Then finally we'll convert the frequency domain signal to time domain signal, and our final result is to see what is the difference in the time domain frequency, what is the width of the time domain frequency. So let's go step by step. So let's go to the MATLAB code. What we did is so in the MATLAB code, what we did is that from the first we have calculated what is the duration of the time domain signal, and we have loaded the Thorlab data, and we have plotted all the data. So important part is here. So this is the very important part, that from the time domain signal that we collected, we know that what is the time for each point. So frequency will be, Fs will be 1 divided by t. We multiplied with e to the power 9 because we converted all the time in nanosecond, because our signal is in nanosecond level. Then this is your initial signal, time domain signal. This is the length of the signal. Now as the basic rule, we have to convert, we have to see the next 2 to the power n size of data. So we found the n is the number of points. Then we did the FFT, and these are just to show the data in FFT. This line will confirm that how the FFT look like. Now important thing will be start from here. As in time domain signal, we have lots of frequencies, but after applying, when the signal will pass through the low pass filter, it will only allow the frequency that's in the frequency response here. So it will allow from here, like all these frequency will be allowed to pass. So we have to find the range of the frequency that will be allowed in the low pass, that will be allowed by the low pass filter. So we find out that what is the starting frequency range, what is the end frequency range of our time domain data. So these are two data. So the frequency range that will be allowed is this original F. This is the time domain signal that we will send, and this frequency range that will be allowed. Now here is the term where we have to match exactly the frequency range of Thorlab data with our time domain data. So we are interpolating the Thorlab data, Thorlab frequency. This is f card is the frequency range that we found. So this f card will keep the corresponding response, dB response in interpolated data. This f card. Now what we have to do is we have to use this response. As we know that frequency domain data has two parts. One is the left part, I'm calling it the left part. There's the real part. So that's my interpolated data within the frequency range of this frequency range. So I'm multiplying my y. Here y is, if you notice, the y is the FFT data. So you have to multiply this FFT data with only which portion? Those portion that the low pass filter will allow to pass, not the whole portion. This interpolated data is the frequency response of the low pass filter, and this is exactly matched with this index range because we have done the interpolation to match the exact frequency. So this is the left part, and in the right part we have to do the same thing. As in the part 1, I have mentioned that in the frequency domain, that the last part of the last signal of the frequency domain is the imaginary part. So it start oppositely. Last point actually is the first point of the imaginary data. So I have to flip the data of the interpolated data and multiply exactly the same index, this same index range. To do the same index range, we did the similar way of these data, in minus index range plus 1, the way that we did in part 1, and then say if you bring that one here, exactly here, and then so this is the last data point, then if you minus the length of the frequency range, that means you are covering the whole thing, and here you are putting your right part of the data. First you have done all the zeros y, that means actually in your data now you have first defined a zero matrix, and you are putting the frequency portion of the data which the low pass filter will allow, both the left side and right side. So these zeros y will have the data at the some portion of the left side of the data, some portion of the right side of the data, and in the middle will be all the zeros. It doesn't matter if we do the IFFT, then we will find the time domain signal again back. But as our length is L, our initial data length was L, time domain length was L, but as when we do the IFFT, there was some zero inside the data, so we have to remove the zero. So we remove the zero here, and this is the final output. So these are the way actually you can generate the signal, generate the output. This is one of the application that's very exciting, that you can use all the data. So already I mentioned that how things work. This is our final goal, that this is the final data where we see clearly that the red data point is the initial time domain data, and this is the frequency domain data. So the white already increased a lot. So this is the way you can choose the low pass filter, which one you like. So to change these things, you have to use different type of filter, like the different type of data, different type of low pass filter, and finally you have to see like which one, say EF 5/10, this doesn't match, EF 5/16, this doesn't match, only EF 5/08 that match our requirement, because duration is here is 588 nanosecond, and this one is, if we took at this 2 point, is 1180 nanosecond. our original data has the width of 500 nanosecond, so it increased almost double, so it's fine, it's pretty good that we can detect. Our original signal has 378 nanosecond, but if we look at our final data, it has a width of over 1100 nanoseconds, so it increased almost 4 times. So that's the way you can increase the width of the time domain signal by low pass filtering.